In this video, we'll talk about the second type of descriptive statistics, which are measures of dispersion. We talked about the mean, median, and mode, which are the measures of central tendency. Even though they provide useful information about the data, they don't tell you everything about the data that you recorded because they don't tell you anything about the amount of spread or dispersion in your data set. And if you want to know how spread out your data values are from each other, you have to calculate another value called a measure of dispersion. There's actually 4 different types of measures of dispersion, and you have to calculate at least one of them to be able to get an idea of how much spread or dispersion is in your data. We'll go over the 4 measures of dispersion one at a time. First, let's talk about the meaning of dispersion or spread. We'll actually go over a few different data sets and try to decide which of those data sets has the lowest dispersion and which has the highest dispersion. And that'll help us get a little bit of a better idea of what dispersion means. And then after that, we'll go over the formulas for the measures of dispersion. So let's decide which of these data sets has the highest amount of dispersion. Each of these 3 data sets are 5 values that have been recorded from 5 people. And these numbers can be whatever you want them to be. For example, they could be the heights of 5 people, because these are really just 5 numbers that I made up, but we could maybe imagine that these are the heights of 5 people, these are the heights of 5 people, and these are the heights of another 5 people in inches. So these 5 numbers are the closest together. They're all between 60 and 64. So these 5 data values have a pretty low amount of dispersion. They're not very spread out. These 5 values in here are a little bit more spread out because we have a 58 and we have a 66. So in data set 2, we have a little bit more dispersion or spread. And then in data set 3, we have the highest amount of dispersion because we have a 56 way down here, and then we have these 3 values in the middle, and then we have a 68 way up here. So this one has the lowest dispersion, this one is in between, and this one has the highest dispersion. We can also look at the dispersion of these 3 data sets by putting the values on a number line. In this data set, all of the values were 1 apart in data set 1. So in data set 1, all 5 values are 1 apart. In data set 2, each of the values were actually 2 apart. We had 58, 60, 62, 64, 66. So in data set 2, the values were all 2 apart, which means that data set 2 had higher dispersion than data set 1. In data set 3, the values were all 3 apart because we had 56, 59, 62, 65, and 68. So data set 3 had the highest dispersion because the 5 values were all 3 apart. And I made the values equally spaced in this example just because I wanted to start with a simple example. Next we'll look at another example of 3 data sets, and this time the values won't all be equally spaced. So what if these were our 3 data sets? This one has some dispersion, but not very much. This one has more. This one has a little bit more dispersion because this value, it used to be that the highest value was 68, now the highest value has gone up to 70. And this one has even more dispersion because now our highest value has gone all the way up to about 73. Now let's look at each of the three data sets on a number line. This was data set 1. Here we have two values that are 2 apart, and here we have two values that are 3 apart. Here they're getting more spread out, and here they're getting even more spread out. So one way to think about this is that if you added these gaps between the numbers, these 4 numbers would add up to 10 for data set 1. If you added these 4 numbers, they would add up to 15 for data set 2, and these 4 numbers down here would add up to 9. Well, let's see. Oh, I'm sorry. These 4 would add up to 10. These 4 would add up to 12. And these 4 would add up to 15. So that's how we know that this has the lowest dispersion. This is in the middle, and this is the highest. So how do we, besides just counting, or besides just adding up the gaps between the numbers, how do we measure the spread or dispersion in a set of data? The simplest way to measure the amount of spread is with a range. To get the range, you just subtract the largest value in the data set by the smallest value. So what's the range of these 4 numbers? The highest is 8, and the lowest is 2, and 8 minus 2 is 6, and that's the range. If we had this spreadsheet right here, well, we can see that we already have the mean, median, and mode down here already calculated, but we're actually focusing on the range. So we want to know what's the range of the age column. Well, the highest age is 40, and the lowest age is 20, so the range would be 20, because 40 minus 20 is 20. When you subtract the highest by the lowest, you get a range of 20. This column actually has no range, because you can't find the range of categories, because you can't subtract the highest and lowest values. You can't subtract upper class by lower class, so there's no range. And over here, there's also no range because you can't subtract. Well, if it's nominal data, there's actually all values are equal, so you don't even have a lowest and a highest value, so there's no range. Now let's talk about the 2 problems with the range. One problem is, just like the mean, it's highly affected by extreme values. This data set has a range of 5, because 25 minus 20 is 5. But what about here? If we change the highest number from 25 to 1,000, the range goes all the way up to 980. Because now we're subtracting 1,000 by 20, which equals 980. Also, the range only shows the distance between the highest and lowest values. It doesn't show anything about how much spread exists in between those 2 values. So here's an example. Here we have 3 different data sets. Right here, the 3 middle values are 1 apart. Here they're 3 apart. Here they're 4 apart. So the middle values are getting more spread out, but the range isn't going to change, because if the highest is always 15 and the lowest is always 5, the range is will be 10 for all 3 data sets. So the range tells you how far apart the lowest and highest values are, but it doesn't show anything about how spread out the middle values are from each other. So the range doesn't do a very good job of showing the overall spread that exists throughout the entire data set. There's another value that does a better job of showing the overall spread of the data called the mean absolute deviation. The mean absolute deviation measures how far each value is from the mean, and it's basically the average distance to the mean. And I'll explain what I mean by this. First, let's go through the steps for calculating the mean absolute deviation. First, you have to calculate the mean of the data. You have to add the data values and divide the total by the number of data values. Then you subtract each data value by the mean to get values called deviations. And each deviation measures how far that data value is from the mean. Then you find the absolute value of each deviation. What that means is that a deviation can come out to a negative number or a positive number. For example, if the data set has a mean of 60 and a certain value in the data set is 56, if you subtract 56 by 60, you get a deviation of -4. So any data value that's below the mean will have a negative deviation. Also, any value that's above the mean will have a positive deviation, because the mean is 60 and one of the values is 64 inside of the data set. When you subtract the 64 by 60, you get a deviation of +4. So deviations can come out to positive or negative numbers. When you get the absolute value of the deviation, you just take the number and ignore the sign. And once you have the absolute value of each deviation, you find the mean of all of the absolute deviations. Let's go through an example. Let's find the mean absolute deviation of 2, 4, and 6. First, we have to add the 3 data values and divide the total by 3 to get the mean. Remember, the mean is just the total of the data values divided by the number of data values. Since we have 3 values in here, we're dividing the total by 3 to get our mean. And our mean came out to 4. The second step is subtracting each data value by the mean to get the deviations. So here we can have a column for the data values and a column for the mean of 4. And we know the mean is 4 because we calculated it in step 1. If we subtract them one at a time, 2 minus 4 gives us a deviation of -2. 4 minus 4 gives us a deviation of 0. And 6 minus 4 gives us a deviation of +2. And with we see that each data value has its own deviation. And what the deviation shows is how far the data value is below the mean, or how far the data value is above the mean. So this data value of 2 is 2 below the mean of 4, which is why it has a deviation of -2. -2 means 2 below the mean. This data value of 6 is 2 above the mean of 4. So this deviation of +2 right here means that this value is 2 above the mean. This data value of 4 is equal to the mean. So any data value that's equal to the mean has a deviation of 0. And in everyday life, the word deviate means to go off track. So if something is deviating, it means it's going off track from something. So what each deviation shows is how far each data value is going off track from the mean. If the data value is 2 below the mean, its deviation is -2, because it's 2 off track in this direction. And if the data value is 2 above the mean, it has a deviation of +2 because it's 2 off track in the other direction. Once we have our deviations, we have to find the absolute value of each deviation. To do that, we just, if we see a negative sign, we take it off. So if it's -2, it becomes 2. Otherwise, if there's no negative sign, it just stays the same. So 0 will still be 0, and 2 will just be 2. What the absolute, so just like how each data value has a deviation, each data value also has an absolute deviation. The absolute deviation shows how far the data value is from the mean. But the absolute deviation has to be a positive number. So the absolute deviation doesn't show whether the data value is below or above the mean. It just shows how far the data value is from the mean. So this data value of 2, this first data value of 2 is 2 away from the mean of 4, which is why it has an absolute deviation of 2. This data value of 4 is 0 away from the mean, so it has a deviation of 0, an absolute deviation of 0. And 6 is 2 away from the mean, so it has an absolute deviation of 2. So basically, the deviation shows how far the data value is below the mean, or how far it is above the mean. But the absolute deviation is just the distance from the data value to the mean. And the absolute deviation doesn't tell you if the data value is below or above the mean. So if each absolute deviation is just the distance from the data value to the mean, if we calculated the mean of the absolute deviations like this, we would be averaging all of those distances, and we would get the average distance between each data value and the mean. So step 4 is finding the mean of the absolute deviations. There's 3 of them, so we add them and divide by 3, and that's our answer. The mean absolute deviation is just the mean of the absolute deviation column. And here was one other example with a set of 4 numbers. Step 1 is still finding the mean of the data. Step 2 is subtracting each value by the mean. In this case, the mean is 9. We get these deviations. 3 is 6 below the mean of 9, so this is -6. 7 is 2 below the mean of 9, so this is -2. 11 is 2 above the mean, so it's +2. And 15 is 6 above the mean of 9, so its deviation is +6. So 6 below, 2 below, 2 above, 6 above. The absolute deviations just take off the negative signs. So this right here, this 6, just means that 3 is 6 away from the mean of 9. This 2 right here means that 7 is 2 away from the mean of 9. And the same thing here. This 2 means that 11 is 2 away from 9. And this 6 means that 15 is 6 away from the mean of 9. These are just the distance from each data value to the mean. By averaging them, we get the average distance to the mean, which is the mean absolute deviation. Now I want to talk about why the mean absolute deviation comes out to a larger number when the data has more spread. So here's a demonstration. If every data value is the same, then the data has no spread at all, and the mean absolute deviation is 0. So here we have all 5s. If there's no spread at all in the data, the MAD comes out to 0. But what if these two values drop down to 3 and 3, and these two values go up to 7 and 7. So in our data right here, we have 2 3s and 2 7s. We can see right here in this column that every value is 2 away from the mean, because these two values are 2 away from the mean, and these 2 7s are also 2 away from the mean. Like I said, the absolute deviation is just the distance from the data value to the mean. So if every data value is 2 away from the mean of 5, then the absolute deviations will all be 2 right here. And if all of the absolute deviations are 2, the mean of those absolute deviations has to be 2. So now our MAD has gone up to 2. But what if this value drops to 2 and this value goes up to 8? Now we have one data value that's 3 below the mean of 5 right here, and one data value that's 3 above the mean of 5 right here. Now 2 of our absolute deviations have increased because these values are now further from the mean, which means that the mean of these 4 absolute deviations is going to be bigger than 2. We can see that the MAD has now gone up to 2.5. Because the mean of 2, 2, 3, and 3 is 2.5. So, yeah, if half the values are 2s and half of the values are 3s, like 2, 2, 3, 3, the mean is 2.5. Because that's halfway between 2 and 3. Okay. Here, if our absolute deviations go up to 3, 3, and 4, 4, then the MAD will be even higher. So basically, as the data values get more spread out, the absolute deviations get bigger, and that causes the MAD to increase. The fact that the absolute deviations are getting bigger is what's causing the MAD to increase. So I'm summarizing that right here. When the data has more spread, the absolute deviations get larger, and the MAD gets larger, because the MAD is just the average of the absolute deviations. It's the mean of the absolute deviation.